Hello everyone. For this week's tutorial, I'd like to go over the basic waveforms as well as the most fundamental properties of sound, frequency and volume. The most basic of all sound waves, in analog form, is called the sine wave and looks like a series of hills that repeatedly goes up and down. This wave represents how air pressure fluctuates, as all sound waves do. And in this case, the air molecules vibrate back and forth smoothly and constantly. And in this case, this is what the sound wave will sound like. This fundamental waveform is also very easy to demonstrate frequency and volume with. The frequency determines how many cycles there are per second, which in everyday terms means how many times the air moves back and forth per second. In general, the higher the frequency, the more high-pitched it will sound. And the lower the frequency, the more deeper the sound will be. If you zoom in on the wave close enough, you can also count the frequency manually by determining how many times it moves back and forth in between 1 second. The other fundamental property of sound, volume, refers to how loud the sound is. Just like frequency can easily be visualized by determining how many times there are cycles in 1 second's range, volume can be visualized by determining the difference between the highest and lowest points in the sound, in this case, the peaks of the hills. Example of sine wave with louder sound. Example of sine wave with quieter sound. Even though I have described frequency and volume in everyday terminology to make it easier for the viewer to understand, if you wish to be a professional musician or sound designer, you would have to be familiar with the scientific terminology as well. In which case, frequency will be referred to as hertz, written capital H lowercase z, to determine the number of cycles per second. And volume will be referred to in decibels, lowercase d uppercase b. Although the caveat is that decibels use what is known as a logarithmic scale rather than the traditional linear one. This means that an increase in 10 decibels does not mean it is 10 times as loud as you might think, but actually only twice as loud. By similar logic, 100 decibels does not mean 100 times as loud, but 3 times as loud. 1000 decibels means 4 times as loud, 10,000 decibels means 5 times as loud, and so on. This means that any decibel level that does not fall neatly on a power of 10 will give you a messy decimal number rather than a neat number. And the other caveat when using decibels versus hertz is, hertz is what is referred to as an absolute measurement, i.e., it will always refer to the same pitches, regardless of what exact sound you are working with. Whereas decibels is what is referred to as a relative measurement. That is, decibels refer to the change in volume relative to the current sound you are working with, rather than an absolute measurement that applies to all sounds. So 0 decibels does not mean absolute silence, but instead means no changes relative to the current volume. And you can also have a negative decibel amount, which means a decrease in volume relative to the current amount. So far, I've been using the sine wave to demonstrate the sound wave concepts, because it is traditionally the fundamental sound wave in analog form. But since basically all electronic devices nowadays are what's referred to as digital, they use a different fundamental sound wave to create complex sound waves. This fundamental wave is called the square wave and looks like this. Regardless of what wave we are working with, frequency and volume apply the same always. But since the square wave uses binary ones and zeros, i.e. it is either 100% volume or none at all, no smooth transitioning like the sine wave, it will therefore have a much different sound, which has a much harsher tone. Like this. The next fundamental waveform is the sawtooth wave, which is sort of a cross between the binary properties of the square wave and the analog properties of the sine wave. The waveform looks like this, and as you can tell, it smoothly transitions to its lowest volume, but does not do the same when going back up to its highest volume. It will do a binary jump instead, like with the square wave. Because of this, it will produce a tone like this. Next fundamental sound wave I like to explore is the triangle, which is like the sawtooth, but is even more analog and even less digital. The triangle wave looks like this, and as you can tell, it transitions both up and down. There are no jumps along the wave. However, just like with the sawtooth transition, it is much more sharper than the sine wave. So in turn, you will hear a sharper sound, like this. The next fundamental sine wave is not as commonly talked about, but is still very important, and is referred to as the semi-sine wave, and looks like this. It is very similar to the sine wave, except all of its fluctuation points are at the same exact volume. It does not go back and forth, positive and negative, like the sine wave does. So mathematically speaking, it can be thought of as the absolute value of the traditional sine wave function. Because of this special property, the tone will sound like this. The last fundamental sound wave type is the pulse/rectangular wave, which is the same as the square wave. You may notice how with the square wave, it is 50-50, i.e. the loud and quiet parts are the same exact length. However, with the more general rectangular wave, the patterns will be uneven, so the louder parts can be longer than the quieter parts, or vice versa. The reason why I said pulse/rectangular earlier is because you may hear in technical and scientific fields how rectangular waves are called pulse waves, as that is the industry name for them, although I would prefer to stick with rectangular waves to make it easier to understand. I can discuss how digital recording works next week, more specifically how a microphone works, what sample rate is, more specifically how a microphone works, what a sampling rate is, and what bit depth is, and how it's similar to bit depth in colors for digital graphics. Don't forget to subscribe if you found this video informative, and make sure to visit the other tutorial videos, and follow me on either Facebook or Twitter for more content.